Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is 4-layer board communication module design, harmonious coexistence and isolation of RF and digital circuits. It's a pleasure to learn together. Welcome back to our series on the features of 4-layer board communication module design. In the previous video, we discussed why isolation is necessary between digital and RF designs in modern systems. Today, we'll put that theory into practice. Through a specific example, we'll demonstrate how to achieve harmonious coexistence between digital and RF modules on a 4-layer board, enabling them to work closely together while avoiding mutual interference. The physical isolation strategy for digital and RF signals is key to successfully integrating communication modules on a 4-layer board. The core lies in physical separation. The first principle is partitioning. The basic rule is to clearly separate the digital circuit area from the RF circuit area right from the PCB layout stage. Typically, the RF circuit is placed on the opposite side, far away from high-frequency digital signals. As you can see in this circuit, the division is very clear. It's split left and right. The right side is entirely the RF section, while the left side is the digital section. In the middle, there are only a few essential empty signal lines crossing through. You need to avoid crossings as much as possible. Try to prevent digital signal lines and RF signal lines from intersecting, especially keeping high-speed digital lines away from RF lines. In this example, it's very clear. All the digital circuitry is integrated in this section, including the main components and power supply, which are kept far from the RF side. Only a few necessary communication lines connect the two areas. Next, for power isolation, you should first use independent power supplies. Whenever possible, provide a separate power supply for the RF module. Even if the main power supply is shared, you must strictly manage the power input at the RF module, for example by using cable ferrite beads and multiple decoupling capacitors. This capacitor is also very well designed. Its power supply comes from the UMB provided module. Then, as we can see in this area, this is a power module. This is the input power module. Here there is a common mode cable that connects the 5-volt line and GND, isolating the analog and digital grounds. This part is the power supply section of the design. So these are two completely independent power supplies, 3.3 volts each, fully isolated. We can also see this on the schematic online. If we look here and set it to level 3, we see that the right side is labeled AVCC 3.3 volts and the left side is DVCC 3.3 volts. This indicates that the digital and analog power supplies are isolated. At the same time, for the grounds, the left is digital ground and the right is analog ground. Both the power and ground are completely isolated. The power plane also needs to be divided. In some cases, the power layer can be split to create isolated power regions for RF to prevent interference. But please note that the power split must be consistent with the continuity of the ground plane to avoid crossing the split line. As we just saw, their split line is right in the middle, dividing the left and right power and ground at the same time. Isolation of the ground plane is also extremely important. On a 4-layer board, a complete ground plane like L2 is crucial. Not only does it serve as the return path for each signal, but it also acts as a natural isolation barrier. Stitching wires, ground slots, or ground fences can be placed densely along the boundary between the RF area and the digital area, forming a ground fence or ground wall to further enhance isolation and enclose the RF section. As we can see, on the RF side, a ring of ground wires has been placed all around, which also helps reduce external radiation. Optimizing the RF signal path. Why does it need to be short? The design of the RF signal path itself is also very important. The first point is impedance matching, which we have discussed before. RF signals must have strict impedance control, usually 50 ohms. This means you need to precisely calculate the trace width, spacing, and the distance to the reference plane. This is what we talked about earlier regarding how to calculate impedance. And then keep it short. Also, keep the RF signal traces as short and straight as possible. Avoid unnecessary bends or any changes in length or direction, as these can introduce impedance mismatches, leading to insufficient signal integrity. You can see that there are three aspects to this. The RF output interface, right? This one that's directly aligned is a perfect example of a straight line connection, which is ideal. However, because these two components are very close together, it's not possible to place them any closer, and putting them too close would also cause some circuit interference. So by spacing them apart, this trace can no longer be perfectly straight. As for this trace, it's for the crystal oscillator, which is a 25 megahertz crystal signal. Since it's just a copy of the signal, it doesn't require as much control as the other two traces. Essentially, this serves as a reference point. As long as impedance control is maintained, the IF trace can be made appropriately wider to reduce loss. For bends, large radius curves should be used instead of right angles to keep the impedance continuous. This is quite obvious here. All of our traces that have been bent use rounded corners, not 90-degree or even 45-degree angles. However, for this 25 megahertz reference, since its requirements are relatively lower, it uses a 45-degree bend. There must be a complete and continuous reference ground plane beneath the 2F signal line. Any discontinuity in the ground plane may cause a drop in the 2F signal. As we just saw on the non-layered side, the ground plane is very complete. This is the reference design we are providing this time, ordinary in every aspect, but up to standard in design. Today, through the case study of an integrated communication module, we demonstrated how to reasonably set digital distance signals on a 4-layer board, including partitioned layout, noise-free power supply, a complete ground plane, and key strategies for optimizing RF signal routing. Mastering these techniques will help you design high-performance, stable, and reliable communication electronic devices in the trend toward integration. I hope this content is helpful to you. If you enjoyed this video, please subscribe to my channel for more videos. Thank you, everyone.